Given the graph original function going to the derivative. So you want to evaluate the slope. So the slope on this one is always the same. Yes? It is, if I'm guesstimating, well, there's a point, and then let's just say 1/1-ish, so up 2 over 1. So the slope is, let's say, constantly 2 because that's linear. So your derivative function is just going to be that. Now, I did a little faux pas there because this function doesn't have arrows on the end of it, so my derivative shouldn't either. What is the derivative right at the end point? What is the slope right at the end point? Does not exist. So an open circle at the end of that, and right at the end point here, it also does not exist. So just paying attention to that little detail. On the next exercise, same thing, although if you want to, do you want to, just because none of these have arrows, I'll just put arrows on the end of that original function just so we can not worry about that so much. So I think any place on the original that you see a slope of 0 is going to be a root of the derivative. So there at negative 1-ish, at 0-ish, and at positive 1-ish, we have 0 slopes. Slopes of 0. So on our derivative graph, those will turn into roots. Prior to this, what is our slope? Negative, right? The function is decreasing, so our slope is negative. So our derivative is in the negatives, aka underneath the x-axis. Then right there, our original function starts to increase, which means the derivative is positive. So if I'm connecting these two roots where the two slopes are 0, it's increasing in between, so there's a little loop into the positives right there. And then in between these next two zeros, the graph is decreasing. So the derivative should be in the negatives, aka underneath the x-axis. So there's a little loop wrapping around there as well. And then from this point forward, the graph is always increasing, so my slope is always positive. And you really can highlight there the fact that your original function was a 4th degree and your derivative is a 3rd degree. Yes? Okay, this one is a little bit trickier because, and again, we can assume that we have arrows on the end of that. Just put them there to make our life a little less complex. There seems to be something critical happening at 0. Yes? Okay. What is our slope at 0? Undefined, right? It's got one of those vertical wiggles. So it's instantaneously going vertical. What is your slope way over here if you had to guesstimate? What's that? It's right. It's positive or negative. Let's start there. Our slope is positive and slightly positive, and then it's getting more and more positive until it's pretty much infinitely positive right before it's a perfect vertical swivel. You follow? So we have a positive slope that's not very positive here. It's getting more and more positive here, and then it's really approaching infinity. As you get closer to a perfect vertical curve, your slope is a humongous number. And then if you come out of this, what is our slope here, positive or negative? As soon as we come out of it, still positive. Very positive or slightly positive? Very positive again. So again, we have that infinite behavior. And then it's becoming closer and closer to a slope of 0, but all the while positive. So it's pretty much the same thing on either side. Okay? So that should be somewhat of a review, a refresher. This is using the graph of the derivative. So always pay attention to what graph you're given. Are you given the original or are you given the derivative? This side, this is the derivative. We want to identify the intervals on which the function, the original function, is increasing. So the original function is increasing when the derivative is positive. So a positive derivative, since we're looking at the derivative, means above the x-axis. Are you with me? Again, let's put arrows on the end of this just for the sake of simplicity. This derivative is positive, which means the function itself is increasing from negative infinity up until negative 1. Right at negative 1, it's neither increasing nor decreasing, right? So it's probably a relative max or min is my guess. And then after negative 1, so from negative 1 to infinity, our derivative is in the negatives. If your slope is a negative, then you are decreasing. Estimate the values, so that would be part A. Part B, estimate the values of x at which f has a relative max or min. So would that be a relative max or min? If it was a positive slope into a negative slope. Max. Did you say min, Josh?
Yeah, but I don't know why I said it, because I know it looked like it upside down forever.
Okay, so that's a max. So max, relative max at negative 1. Okay? Next one. So I'll just set it up for increasing intervals and decreasing. So again, let's put arrows. So what is our original function doing based on the fact that the derivative is here between negative infinity and negative 1? Stephanie, what do you think? Increasing, right. So because the derivative is positive, the original function is increasing from negative infinity to negative 1. And then here our derivative is negative, which means the slope is negative on the original function, which means it's decreasing from negative 1 to 0. And then my derivative goes positive again, so my function is increasing again from 0 to 1. And then my derivative goes negative again, so it is decreasing from 1 to infinity. I don't know if, as far as for part B, if it would be more helpful for you. Obviously, we have critical points at negative 1, 0, and 1. And we know here it's increasing, then it's decreasing, then it's increasing, then it's decreasing. If that's more helpful to see it that way for relative maxes and mins. I mean, a lot of you won't need to do that, but if you want something concrete, that's an option. So it's increasing and then decreasing. So we have a max, then a min, then a max. And these are all relative. Any questions on that? They want us to sketch a picture, I believe. Oh, do they? No. These two go together. Okay. F is differentiable for all x values. So they're telling us that the derivative is positive from negative infinity to negative 4. In other words, what does that mean about the original function? F is increasing. The derivative is negative, means obviously f is decreasing. And if the derivative is positive, f is increasing again. So if you wanted to sketch, that might help you kind of wrap your head around it. From negative infinity up until negative 4, we're doing something. Then from negative 4 to 6, we're doing something else. So we are increasing until we get to negative 4. Then we are decreasing until 6, at which point we are increasing again. Anytime you're going backwards, the location doesn't matter, but the general shape should be there. Stephen?
Would you ever have derivative
They could tell you that, but we could gather that that's happening at -4 anyway.
What would you say about the original?
The original, it's a relative max or min. If the derivative equals 0.
Then you know
As long as it changed from increasing to decreasing or vice versa. If it was increasing and then the derivative was 0 and then it was still increasing, then that wouldn't be a relative max or min because it would be something like that. Increasing, slope of 0, and then increasing again. So you have to have the switch from plus to minus or minus to plus if it's going to be a relative max or min. So then fill in the blank with the appropriate inequality sign for each indicated value of C. So they're redefining a g of x, which is taking our f of x function, stretching it vertically by a factor of 3, and then shifting it down 3 units. And then asking you, what is the derivative? In other words, is it going to be greater than 0, positive, less than 0, negative, or equal to 0 at -5? So right at -5 currently, what is it? Is the derivative there greater than 0 or less than 0? Greater. This is your function, a potential version of it. And regardless of whether this is up, down, and shifted, at -5, it is positive. It is greater than 0. What's going to happen to our function if we stretch it 3 and then shift it down 3? Is it still going to be increasing at -5? Yes. Vertical movements don't change anything. So the slope at -5 is still positive. So on this g of x, on the second one, they're redefining it as a vertical reflection. So you're flipping it upside down. So if we were just to flip this graph upside down, it would look like that. That would be your g of x function. So what is the slope at 0 now? Positive, yes? Okay, that does flip it. Anything negative is positive, anything positive is negative. And then a horizontal movement, and you can sketch pictures of your new graph like I just did in that last one. We're shifting it right 10 units. So this relative maximum that was at -4 is now going to be where? If we shift this graph right 10 units. 6, right? That's going to be over here. And this relative minimum at 6 is now going to be at, if you shift it right 10 units, it'll be at 16. So we have a relative max at 6 and a relative minimum at 16 before it starts increasing again. So that's our new g of x function. G prime at 8, so here's about 8, is positive or negative? Negative. Because it's what is the slope doing, right? This is the function g. This is asking what is the derivative at 8. And since it's the derivative, they want what is the slope is 8 at 8, and that is negative. It's just really reading with the critical eye. The concepts aren't that hard, but you can see why. Obviously, it can get confusing if you're talking about the function or the derivative of the function, but you just have to read it very critically and take your time with it. All right, the last one. A function f is differentiable on the interval from 0 to pi. The table shows the values of the derivative. So these are not the values of the function itself, but these are the values of the derivative. So at 0, what could you tell me about the graph? It's increasing. At pi over 6, you could tell me that the graph is decreasing. So obviously somewhere in between there, it had to have turned around, right? A pretty positive slope if you wanted to kind of sketch 0 to pi. Here would be pi over 2. Here would be pi over 4. Here would be 3 pi over 4. Pi over 3, pi over 6. Oh no, I put pi over 3 in the wrong spot. Pi over 2. 2 pi, oh man, a common denominator would be lovely here, wouldn't it? If I really want to do this. 2 pi over 12, 3 pi over 12, 4 pi over 12, 6 pi over 12, 8 pi over 12, 9 pi over 12, 10 pi over 12, and 12 pi over 12. I'm changing my mind. I'm doing it that way. 12 pi over 12. 6 pi over 12. 9 pi over 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There. All these denominators make my life tougher. All right, so right at 0, we have a pretty positive slope. Pretty positive. At 2 pi over 12, we're slightly negative, which means we probably just turned the corner, right? So by pi over 6, we need to be slightly negative. So we'll do something like that. Slighter than this was positive. At pi over 4, which is 3 pi over 12, we're even more negative, so it's steeper than it was. At pi over 3, which is 4 pi over 12, we're even more negative. So it's still getting steeper yet. Then by pi over 2, we're slightly positive again. So at some point, we've just kind of turned around and we're slightly increasing again at pi over 2. At 2 pi over 3, which is 8 pi over 12, by here we're very positive. At 3 pi over 4, which is 9 pi over 12, we're still pretty positive, but not quite as heavily so as we were before. And then by 5 pi over 6 or 10 pi over 12, we're pretty negative again, so something like that. And then at pi, we're more extremely negative than we just were. Now that's just a sketch, but that's approximately what's happening. So sketch the graph, approximate the critical numbers. So critical numbers are where your slope is 0 or undefined. It's never undefined, but it's 0 somewhere in between 0 and pi over 6. So I would say, well, pi over 6 is 2 pi over 12. So maybe like, and it says approximate, so don't get wrapped up in this. So if it's decreasing there, increasing, and this is 2 pi over 12, maybe we would approximate pi over 12. And then critical down here. So anytime there's a shift between negative to positive, this one's going to be closer, much closer to pi over 2. So 6 pi over 12, let's just say 5 pi over 12. We'll keep everything in terms of 12. Positive, positive, positive. Then we're negative again here. So somewhere right, kind of between 10 pi over 12 and 9 pi over 12. Uh-oh. What are we going to do there? 9.5 pi over 12, which you can't do. You can't have decimals in there. So 9.5 pi over 12, just multiply both by 2, so it would be over 24.
19 pi over 24.
19 pi over 24. That's a decimal within a fraction is a complex number. So anyway, that's just approximating, just looking at positive to negative and kind of wrapping your head around how a chart can show you all of that. So there's your homework. You are going to have a test next Friday. So we're pretty much nearing the end of the chapter. The review sheet for the chapter is online. Jalen, what would you say? Can you do all of it already?
I don't know how to do concave stuff.
Concavity is the only thing. That's true. Second derivative stuff, concavity. Other than that, in the review packet, you're pretty well set if you want to get started on that because you have, obviously,
Wait,
All